Whenever an adapter has a frame to send, first it has to sense the channel, and it has to sense the channel idle for 96 bit times. So this corresponds to 9.6 microseconds if we are dealing with 10 Mbps Ethernet. Why this wait? Just because it gives an opportunity for the receiver to process the previous frame before it is ready to receive the next frame. If you remember, when we talked about the frame structure of Ethernet, I was mentioning an interframe gap. So this corresponds to the interframe gap. Now, as soon as it finishes this checking for idle time of this duration, it starts transmission. But if it found the channel to be busy, it waits until the channel becomes idle and then additional 96 bit times, and then it is going to transmit. Because it is one persistent, there can be collisions. But if no collision is detected as part of the ongoing transmission, the frame transmission is deemed successful and the adapter is done with that particular frame. But however, if it detected a collision during the transmission of the frame, the adapter will stop the transmission, send the jamming signal, and enter what is called exponential backoff. Basically, this dictates what is the random time the adapter has to wait before it tries to retransmit this particular frame again. So here is exponential backoff details. So when you are transmitting a frame after the nth collision, you basically wait for k times 512 bit times, where k is chosen random within this interval, where this value m is given as minimum of n, 10. So let me give an example. So for example, a frame was transmitted, it suffered a collision. So that was the first collision that it suffered. Then this node is going to choose a k between 0 and 1. If it chose a value of k 0, then it is going to try to attempt transmission of the frame right away after waiting for that 9.6 microseconds. Whereas if it were to choose a value of 1, it will wait for 51.2 microseconds and then attempt the transmission. But during this time, if it were to detect that the channel was busy again because someone else chose a value of 0, then it will again have to wait till the channel becomes idle and then repeat the process. What if it transmitted again and that also suffered a collision? This will be the second collision. In this case, the node will choose a value of k between 0, 1, 2, 3. And this goes on where after the 10th collision, chooses k between this value, and then it keeps this range constant till the 15th collision. In other words, the maximum number of transmissions for a frame is restricted to 16, which involves one original transmission and 15 retransmissions. So as you see, the size of k is growing exponentially after each collision. So why this exponential backoff? In other words, what is k trying to capture? Basically, k is trying to capture the current load. If the load was low, small values of k will suffice, because you don't really have to wait for a really long time to access the channel. But when the load is high, this is going to result in lot of collisions. And if you were to choose a small value of k, for example, if there are 10 nodes trying to transmit a packet, and if you chose k is equal to 0 and 1, everyone is bound to collide. So this won't do. You need a much larger k. A given node has no way of knowing what the load on the channel is. It has to get this feedback from the channel itself, the behavior it is observing on the channel. If it is experiencing lot of collisions, that means the load is high, thereby it will start choosing a larger value of k. If it is not experiencing that many collisions, that means the load is less, thereby it chooses smaller value of k. And where did this 512 bit time come as part of exponential backoff? Basically, this gives an opportunity for a node which chose a lower value of k to transmit without collision. For example, node A chose a value of k is equal to 0. Let's say node B chose a value of k is equal to 1. So k has started its transmission and it's kind of ongoing. Now B is going to wait for 51.2 microseconds before it is going to listen to the channel to decide whether it is idle or not. The why it has to wait for this time is it has to allow for the propagation delays, in other words, for A's bits to reach B so that B can detect that there is an ongoing transmission and not transmit. This value ensures that all nodes in the network can hear A's transmission and thereby not transmit. And this happens if they wait for at least 51.2 microseconds. So what is Ethernet's efficiency? Don't worry, I'm not going to derive this expression. It turns out that when there are large number of nodes with large number of frames to transmit, the efficiency is a function of the propagation delay. This is one-way propagation time between two nodes in a LAN and the time it takes to transmit a frame. If this propagation delay is tending to 0, what does efficiency become? So in this case, the efficiency is tending to 1. What is the reason for this? This is because you are now able to detect collisions rather instantaneously, and thereby you are not wasting the channel resources. That leads to very good efficiency. Similarly, if the transmission time TTX is rather large, again the efficiency tends to 1 because you are using the channel for doing useful work. So by carefully configuring the Ethernet, we can maintain very high efficiency. What do I mean by configuration? Basically by choosing very large frame sizes. So typically Ethernet uses 1500 bytes. Also ensuring this maximum propagation time between two nodes is small. So typically you operate under few hundred meters. That is the max distance. So this efficiency equation was derived under large number of nodes. Naturally, when there are more number of nodes, the chances of collision are higher. Again, you can maintain high efficiency by ensuring that you have fewer number of nodes per segment, by which I mean within the same collision domain. Even though the maximum limit is 1000 hosts per collision domain, typically Ethernet operates under 200 hosts. So if you did all this, you can always maintain an efficiency which is greater than 85%. To summarize, the CSMA family of protocols improve upon Aloha. There were two persistent and non-persistent CSMAs, and there are trade-offs involved here. Ethernet MAC employs one persistent CSMA and adds this feature, collision detection, to improve performance. And as you saw, if your collision detection is very good, you can maintain your efficiency rather high because you are not wasting the resources anymore. Now this collision detection definitely needs additional functionality in terms of hardware support. It also places restrictions in terms of the length of the cable, frame size, so on, as well as the number of hosts that can be part of the particular system. But by appropriately configuring Ethernet, you can achieve good performance. All said and done, within a collision domain, the maximum number of hosts you can support or the network diameter that it can take is rather restricted. If you want more number of hosts and larger network span, you need to do something different, that is Ethernet switching, which we will cover in the near future.